Hi everyone. So here is the final lecture for the module 4. So it's lecture 5 about electromagnetic induction and Faraday's law. What do you see from here? Um, what you see here at the last picture, it is the dam, and in which it is the power plant, water power plant, in which we use the kinetic energy from water flow, kinetic energy, and we convert this kinetic energy into electricity, and then we give the flow of electrons to household, and we use the energy from the electron for our use. Okay, so how can we actually transform the kinetic energy or the motion of water into the electric energy? Okay, in this lecture we have the answer. Okay, so let's consider the simple case of a conducting coil and a magnet bar. Here, if you try to move the magnet bar into the conducting coil, what happened is the change of magnetic flux. Okay, so this is a key concept in this lecture. The change of magnetic flux generates or creates the voltage. Okay, so that if I move the magnet bar towards the coil, or if I move the magnet bar outside the coil, we can see the change in the voltage. Okay, so and there is some electricity flow within the coil. Okay, then we try to transform this machine into another form. We have the conducting coil in this form, and we plug that into into the machine so that it can rotate. Then when we rotate the conducting coil under a magnetic field, okay, we can see the same phenomena. We see the change in magnetic flux, and the magnetic flux will generate the voltage, and the light goes up. Okay, and the same principle is applied for the power plant, in which the kinetic energy from the water will turn the conducting coil within the magnetic field underneath the dam, underneath the generator, and then the electricity is created here. Okay. Okay. So what are we talking? What are we discussing? We start with discussing about magnetic flux, and then we discuss about Faraday's laws and Lenz's law, in which the change of magnetic flux, or if I say it's a delta of magnetic flux, will generate the delta of magnetic flux and divided by the time is can be written in terms of the electromotive force in the unit of volt. Okay, and then motional EMF. Motional EMF is the EMF or electromotive force that is generated by the motion of some objects. And finally, we discuss about electric generator. Magnetic flux. So the definition of magnetic flux is related by the magnetic field and the area. Okay, so magnetic flux is defined when a magnetic field is passing the area A, and we define the magnetic flux as the integral. Okay, so it's the B dot dA. Okay, and A is defined by a vector that is proportional to the surface. Okay. If we consider the vector A here, the vector A is perpendicular to the area. So that if B and A are parallel, or B perpendicular to the surface, just like in this case, the dot product become the times, okay? Become just the product. And with a uniform magnetic field, so if B is a constant, we pull it out from the integration, and then finally we have flux equals BA, or phi B equals BA. Okay, in spatial case, if B perpendicular to the area and if B is uniform. So we reduce this integral into BA, into magnetic field times the area. Okay, let's consider some simple cases of uniform magnetic field. So for the case of uniform magnetic field, okay, the first case is when magnetic field is parallel to the vector A. So this vector is the vector A. Okay, so if B is parallel to A, or B perpendicular to the surface, we have that phi B equals BA. But if B is making an angle theta with A, okay, so we have that phi B is BA cosine theta, or it is the dot product between B and A. But if the magnetic field B is perpendicular to A, or theta is 90 degrees, okay, you can see that there is no field line that is passing the blue area, and you can find that the magnetic flux is 0. Okay, so now let's have some calculations on the magnetic flux. Okay, so we're discussing about a solenoid. Okay, so in the last lecture we know how to calculate the magnetic field from a solenoid. So we use this formula that is derived from Ampere's law. Okay, please see the last lecture for this formula. And then this solenoid coil creates the magnetic field B, and we use the magnetic flux as NBA. We have N here because of the field B is passing N areas. Okay, it's passing N areas, because if we consider the coil, magnetic field B is passing, this is the one area, so we call this the 1A. This is another area, we call this another A, and A, 3A, 4A, 5A, and then NA. So that the total area is N times the area A. So flux will become NBA, and we use the B from Ampere's law. So then we have the expression for the magnetic flux. Okay, so finally we substitute all the values. We substitute mu0 as 4 pi times 10 minus 7. We substitute number of turns N. We substitute the current I. We substitute the radius of the solenoid, and then we divide it by the length of the solenoid, so that we have the magnetic flux in the unit of Tesla meter square, or we call this unit the Weber, or WB. Okay, and we are going to revise this example again in the example class. Okay, so we have discussed about magnetic flux already. So now we come to the topic about induced electromotive force. As we discussed before, the change in magnetic flux will create these words, electromotive force or EMF. So electromotive force, we can discuss about EMF in terms of potential difference, or in the unit of volt. Okay. So the main idea is the changes in magnetic flux induce electric field. So how are we changing the magnetic flux from this picture? So we change this magnetic flux by moving the coil in or out. Okay, so moving the coil in, you can see the different number of magnetic field lines that going past through this coil. And moving the coil out, you're also going to see the changes in the magnetic field lines that passing through the coil. And as a result, there is the voltage or electromotive force or EMF, or we simply call it E, to flow around the coil. Okay, so Faraday's law. So we described this phenomena in terms of equation. So we have the Faraday's law that states that the change in magnetic flux will equals to the induced EMF. Okay, will equals to this magnitude of the induced EMF. We are going to discuss about this minus sign later, in which this minus sign will tell you something about the direction of the electromotive force. Okay, so and Lenz's law. So Lenz's law is the idea that make us understand about the direction of EMF generated by changing influx. Okay, so we use Lenz's law to determine the direction, and Lenz's law states that the induced current or induced EMF, okay, must be in the direction that generate magnetic field to oppose the change in magnetic flux. Okay, so generate magnetic field to oppose the change in magnetic flux. So the idea of being opposite, this is why we have the minus sign here. Okay, so let's see some examples here. Okay, so for example, if I the example on the left hand side, okay, so if I try to move the magnet bar towards the left hand side here, okay, so moving to the left hand side, okay, I say moving to the left will increase magnetic flux. Okay, so why it increases magnetic flux? Because if I just move the same magnetic bar, so you can see that the larger number of field lines is passing through the coil. So larger number of lines passing through the coil. So that we can say that this is having the increased magnetic flux. So when having increased magnetic flux, the magnetic field that is induced, okay, must be opposite to the direction of the increase. Okay, so if magnetic field or if magnetic field that generate the flux is to the left, the magnetic field that is induced is going to the right. So when the magnetic field is going to the right, using the right hand rule, okay, using the right hand rule, if this direction is the B induced, okay, right hand rule will tell you that the direction of the EMF or the voltage will be according to this arrow. Okay, will be like counterclockwise. But in the opposite way, so if I move the magnetic bar outside, okay, so you might see that that fewer lines is passing the loop. So when fewer lines passing through the loops, we can say that the flux is decreasing with this action. So when the flux is decreasing, the B induced will be in the direction that is opposite to the magnetic field to the change of magnetic flux. Because if it is decreasing, the change in magnetic flux will occur in the right hand side. So that B induced is occur in the left hand side. And then if I use the right hand rule again, okay, so this is the direction of B induced. Okay, so here we can see that the direction of the field, the direction of the EMF will be like in clockwise direction. Okay, so let's try to see the case of the magnetic field in a loop again. So it's for magnetic field in a loop, we have that if we have the current that flows in counterclockwise direction, and here I try to use right hand rule. Okay, right hand rule to determine the direction of the magnetic field. So here I can see that doing so. You having the right hand like this cartoon, and we have the current in this direction. Your thumb will represent the direction of magnetic field that is coming up. Okay, but in the other way, so if you consider the right hand, your right hand at any point, okay, your right hand at any point of the loop, for example, at this point, okay, if you use your right hand and use the thumb as the direction of the current here, you're going to see that you are having the magnetic field in this direction. But if you are considering this point, you are going to have your thumb pointing into the screen, and you are going to have your finger to be in this direction, and your finger will, and then the direction of your finger will tell you about the direction of the magnetic field. So this is a case of the magnetic field in a loop, in which we can use to explain that induced magnetic field. Okay, so let's try to have a look at the case of changing magnetic field strength. Okay, so changing of magnetic field strength, you can see that about changing of the magnetic field strength, the density or the number of field lines is changing. Okay, when number of field lines is changing, you can see that magnetic flux has changed. Okay, so when it increased, this is the increasing magnetic flux. So this is increasing magnetic flux, and then follow. So when the magnetic flux increase, and here you can see that magnetic field is in the upper direction. So with increasing B, we see that the change in magnetic flux occur in the up direction. So when the change in magnetic flux occur in the up direction, okay, we have that the electron we have that the B induced occur in the down direction. So when B induced occur in the down direction, according to the right hand rule, you have your thumb down. You have your thumb down, and you have the induced EMF in the clockwise. Yeah, this one is clockwise direction. Okay, then consider the next case. Now, if we decrease the strength of the magnetic field, if we decrease it, okay. Firstly, we have the magnetic field that is pointing up. So if we decrease the strength, we have that the magnetic flux, the change of magnetic flux, d phi by dt is going down. So when d phi by dt is going down, the induced magnetic field B induced is going up. When you have B induced going up, you use the right hand and then do the thumb up. Okay. When you do the thumb up with your right hand, then you can determine the direction of induced EMF by your fingers. Okay. So now the two cases already. Okay. Then the third case. Here, if I change the area now, when changing the area, okay, so when changing the area here, you can see at the first place, you can see the decrease and followed by the increase of the magnetic flux. Okay, so whenever you see the decrease of magnetic flux, you are going to have that the current will flow in. Yeah. Okay. Let me do this. Let me do this for you again. It might be a little bit difficult. Okay. So when we consider magnetic field, and we see that the coil is spinning in this direction. So when the coil is spinning in this direction, you have that, and the flux is decreasing. So if the flux is decreasing, d phi by dt is decreasing. Then when d phi by dt is negative. So with d phi by dt negative, we have the induced magnetic field in the upward direction. When we have the induced magnetic field in upward direction, using right hand rule, and you are going to get the electromotive force in this direction. Okay, but another half of the motion, okay, where you have magnetic field, when you have magnetic field turning up like this, so you can so the other half of this clip, the the coil is turning up in this direction. Okay, so when the coil is turning up, we see that magnetic flux is increasing. So with increasing magnetic flux, the induced magnetic field will go down. So with using right-hand rule, okay, we have that we have that the direction of the EMF will go in the opposite way. Okay, so now we are going to apply some elements of the Faraday's law in the equation. Okay, in the physics lab experiment, there are coil and that is enclosing the area. That means the equation gives you the area, and is rotated in 0.4 seconds, which is delta t, from a position where its plane is perpendicular to the Earth magnet. So this is number one. Okay, so perpendicular to the Earth magnetic field. So this is the magnetic field, and here the plane is perpendicular to the magnetic field. Okay, so for this case, I expect to see that the flux should be that BA. But if the coil has n turn, okay, 200 turns, n turn, we times this by n. We times the flux by n. And then so it rotates from the position where the plane is perpendicular into where its plane is parallel to the field. So when the plane is parallel to the field, no field lines is passing, so we expect the zero flux. All right. So that's we can find the average EMF by doing the flux of NB times A minus 0, and this should be the number that you get. Okay, so the average. So starting with you having the induced EMF as minus d phi by dt. So if you want to find the magnitude, just the magnitude of the average flux, okay, d phi by dt, if we change this into the average, d phi by dt will become delta phi by delta t, and we already know the delta t. Okay, another question, okay. It is about a coil of radius r. We already have r, we already have n. So with this r, we can find that a is pi r squared because the coil is a circle. And we have b, or magnetic field, as a function of time. Okay, so first you need to find the magnetic flux, right? Then so magnetic flux is equals to NB times A, or maybe NA times B. And then I'll just substitute this B into this equation, okay? So so that's, you have this expression when you try to use the Faraday's law, okay? So minus sign disappear because we do the absolute, right? And then you, with a given function of B, you can just differentiate all this function B, okay? And so that you are going to have the magnitude of induced IMF as a function of time. After that, you substitute the time of 5 seconds into the equation, and you should get this number. Okay, another examples. So it is about our square loop. So this is a loop. Not should it be a square? It should actually be a rectangle. a rectangular loop of wire is moved at a constant speed, V, into a region of a transverse uniform magnetic field, B. Okay, so this one, it will become a little more difficult, okay, as we need to, but the first thing we need to do, okay, is to find the magnetic flux first. Okay, so so if I use W as the width of the loop, and if I use L, okay, as the length of the loop, and then if I define this little distance x, okay, so the distance x, okay, the same as this picture, it is the distance of coil within magnetic field. Distance of coil within magnetic field. Okay, so that if I do flux of phi equals BA, okay. So A, or the area, we are going to count just only this area as A, okay. So that A will become W times X, not W times L, okay. So so then if I want to find the voltage or electromotive force, I'm going to differentiate this equation. And if I have a constant B, if I have constant W, what left in the differentiation is dx by dt, in which dx by dt is V, or the velocity that is given in by the question. Okay, so that this electromotive force will be B, W, and V. Okay, so B, W, and V, and if you substitute B, W, this one, and substitute the V or the speed, you are going to get this number. But how to prove that this direction is anti-clockwise? Okay, we again using the Lenz's law. Okay, so in this case, we are going to say that moving the coil in will increase. Okay, moving the coil in will increase the magnetic flux. So in which d phi by dt, okay, will be in the direction that go inside. Okay, that is direction that goes toward the screen. Okay, so that B induced should be opposite. So when B induced is opposite, the direction of B induced is coming out from the screen. Okay, and then using the right hand rule. So you have your thumb up. So when you use your thumb of your right, when you use your thumb of the right hand, okay, coming out from the screen like this, okay, the thumb coming out from the screen, you can see that the rest of your fingers, here is the rest of your fingers, will be pointing anti-clockwise, and that is the direction of the magnetic field. Okay, and if you have a try on the other two questions, okay, you can find that when the loop is completely inside the region of the magnetic field, the induced EMF is 0, because if this is the magnetic field, and if this is the loop, and when it moved from here to here, okay, there is no change in flux. Okay, when no change in flux, using Faraday's law, the induced EMF is 0. Okay, and then for C, when the loop is leaving the region, so when the loop is leaving the region, you are going to see that this region A becomes smaller. When the region A becomes smaller, the flux become decreasing. Okay, so when the flux become decreasing, applying the same rule, you should get the answer that is opposite to A. Okay, motional EMF. Okay, so it is the EMF that is caused by the motion. Okay, so we are considering the problem that we have an electric circuit. We have a small electric circuit in which there is a resistor R, and there are two conductors. This is the conductors. Okay, so all of these are conductors in which R is approximately 0. So, and then we can actually move this bar. Okay, we can actually move this one. So when we move this one, we can see the change in the area. So changing in the area will cause the change in magnetic flux, and changing in magnetic flux will cause the electromotive force, will cause the voltage, and the voltage will cause the current. Okay, so how to derive this one? Okay, it is actually the derivation of this problem is quite similar to what we did before. So we try to define d phi by dt as BA, as B times A, and the area A, we're considering this region. Okay, we are considering this region because we are going to consider this closed rectangle as a loop or as a circuit. Okay, so that we have A equals to X times L. Okay, L is this direction and X is this direction. Okay, but when we are considering d by dt or differentiation, and B and L are constant, okay, we are going to consider this change in the value X. Okay, so dx by dt will become the speed of the moving bar. Okay, and that the motional EMF can be obtained by the BLV. Okay, so let's consider this example again. Okay, so this example gives you the conducting coil with length L. Okay, they already give you this length. It's placed in uniform magnetic field B. They already give you B, and the rod that cuts the magnetic field. The rod means this guy, and move with constant speed V. So they already give the speed. Okay, so we can use that relation to calculate the induced EMF. Okay, and then we bring this induced EMF to calculate for the current when the resistance is given. Okay, so from the formula that we have derived from the examples. Okay, so the induced current, okay, the induced current can be found by the voltage or the EMF divided by R. So this is just like the Ohm's law. This is just like V equals IR, and we're trying to find the I. And we have the motional EMF as BLV. So we come up with this relation for I. Okay, and then let's consider the pulling force. So the question here is how much force, okay, is how much force is used in order to pull the bar at constant speed. So to pull at constant speed. Okay, we need to consider the equilibrium. Okay, so the F from magnetic field, or the magnetic force Fm, okay, and should be equals to the force that we pull the bar. Okay, so F pull should be equals to magnetic force and the magnetic force. So let's recall the last lecture. That don't forget that this bar is the current. Okay, is a conducting coil, is a conducting wire with a current I, and is within the magnetic field. So when current is in magnetic field, there should be a force that is acting on the bar, Fm. So and Fm is trying to resist. Okay, is trying to resist the force that we used to pull. Okay, so we pull. So we pull the bar this way. There is going to be the magnetic force this way. That doesn't allow us to move the bar very easily. So that's from F equals ILB, and I use the right hand rule. Okay, I use the right hand rule. So this is the direction of I, and then I put my palm face down in as the direction of magnetic field, and then my thumb is pointing to the left. So that is the direction of the magnetic field. Okay, so when the magnetic field is go to the left, you need to pull to the right in order to get the constant speed. And then I substitute the I, or the current, from the induced EMF. Okay, and finally I would be able to find the magnetic force and the pulling force in terms of B, L, V, and R, according to this equation. Okay, and to derive the relation about the power. Okay, so we have the relationship that we derived from the last slide. Okay, magnetic force, pulling force is equals to magnetic force. Okay, and then how to calculate the power that used to apply the external force. Okay, or the power of pulling force. The power of pulling force. So normally we have the definition of power, or P, as the work done divided by the time. Okay, so if I write down the work done in terms of force times the distance, okay, so I can use S over T as the speed. Okay, in case of the constant speed, so that I can write down the P in terms of FV. So when I write down P as FV, so I just bring this term of pulling force to times by the speed V. So that we have this term for the power of pulling force. Okay, but then if we compare with the power loss in the resistor, okay, and for the for P of the electricity, okay, we use a formula I square R. Okay, and so I have the I or the current, and then I try to find, and then I substitute the current square and then times by the resistance R, and then I get the similar term. Okay, so that's we can conclude that the electric power is equals to the pulling force. Okay, so that we can see that pulling, which is mechanical energy, can be transformed into electricity. Okay, and this can be a concept of an electrical generator in which we apply the pulling force, and the pulling force can be changed into the electric power. Okay, so generator principle. So in this problem, so here we are going to change the design a little bit. Okay, so why are we changing the design from pulling in one direction into rotating? Okay, it is because rotation is continuous. Okay, so you can keep rotating your generator like forever, if you like. Okay, but if you try to pull the bar, pull the bar in, and to create the motional EMF, you just need to pull it to the distance, and then yeah, you need to run for it. So it cannot be continuous. So you just change from a translational motion to a rotational motion, okay, in order to create a real generator. Okay, so when we create when we try to use Faraday's laws once again to calculate the EMF from the generator, firstly we try to define the electric flux. Okay, so firstly I start with having this vector is vector A, and I have the vector B of magnetic field. So when B in this direction and A in this direction, and it is making the angle theta. So I can find that the flux, magnetic flux, is vector B dot vector A, and it is BA cos theta, right? BA cos theta. But when we consider rotation, okay, when we consider the rotation of the conducting coil, for the rotation, the angle theta is changing as a function of time by omega t. So that's finally I have the flux in terms of BA cosine omega t, and then I plug in this flux into the Faraday's law. Okay, and that's we can differentiate, and we get the voltage that come out as a function of time. Okay, so when we have the voltage that goes up and goes down, goes up, go up and go down, up and down. Okay, this will actually becomes the alternating current. Okay, so this is the easiest way, okay, to explain how the electric generator is working. Okay, so from the voltage, you can calculate the induced current by the Ohm's law, and you can calculate the maximum power by considering the amplitude of the induced voltage. Okay, so generator becomes very this principle becomes very popular. Okay, you can use the principle of changing magnetic flux when you try to rotate the coil. When you rotate the coil, the angle change. When angle change, magnetic flux change. When magnetic flux change, you have induced EMF or induced voltage. So when you have the induced voltage, you have induced current, and use current to run the lights and everything. Okay, right. So for the electric generator power plant, so it doesn't matter. It doesn't matter how you get the power to drive the turbine. So the turbine, this part, it used to rotate. Okay, so if you consider the generator like this part, yeah, this part. If we zoom into this part, okay, it will certainly consist of coil. Okay, consists of coil that is able to rotate, and then surely you should have a magnet that can generate a magnetic field. Oh, yeah, you have the magnet that can generate a magnetic field. Okay, let me draw this again. So we focus on this part of generator. So in here, we have the coil that can be rotated, and we have some source of magnetic field that can create a magnetic field B. And when you rotate this coil under the magnetic field, it can generate the AC current using the same principle. Okay, and the turbine is the mechanism that you convert some kind of energy into rotational motion. Okay, and then you use this rotational motion of the axle, okay, to rotate the coil under the magnetic field. And when we have the power, we transmit the power to the lines. Okay, or even if you have the nuclear power plant, okay, the principle is still the same. Okay, so for nuclear power plant, you have the reactor. The reactor is where you have the nuclear reaction over here. So when you have the nuclear reaction, it gives you the energy, and you use the energy to boil the steam. Okay, so I can say that, okay, the reactor, yeah, it is delta E equals delta mc square. It is a nuclear reaction, and which you see some we're gonna have some mass disappear, and the mass will change into the energy, and according to Einstein's relation, then we use this energy, okay, to boil the water and create the steam. So that you are going to use the delta E to be Q, to be the heat, and you use either like mc delta T, or you either use a delta ml, and then this mass delta m of the steam coming with some speed, some velocity, like I would say it is a half mv square of the gas molecules, and the half mv square of the gas molecules will run the turbine, will be converted into rotational motion again. Then in the generator, you are having a conducting coil and rotate under a magnetic field, and finally you have and finally you are going to have the electric power, and yeah, you can transfer the power to the houses. Okay, and this explains everything.